Alright class, today we're going to actually solve some differential equations in this video. So we're going to look at this second order linear homogeneous differential equations. This is what I refer to as case 1. The characteristic equation, of course, so our differential equation is ay double prime plus by prime plus cy equals 0, with characteristic equation ar squared plus br plus c equals 0. And I just went one more step ahead further and got solved that using the quadratic formula. And this is how you're going to see there's three cases. So r is equal to negative b plus or minus the square root of b squared minus 4a over 2a. And how do we get three cases? Well, it has to do with that thing inside the square root. And what is that called, that thing inside the square root? No, it's not a determinant. It's a discriminant. Okay, so case 1 is basically just looking at the three signs that the discriminant can be. So case 1 is where b squared minus 4ac is bigger than 0. So what kind of solutions am I going to get to that characteristic equation? That's going to be two real distinct roots. That's R1, and I'm going to call them R1 and R2. Okay? So, let's see. Let me give you, I guess, the claim, and then we'll go through and sort of prove it. Okay? The claim is that the general solution to star, and let me just go back up and remind you that star, the generic homogeneous differential equation is star. Okay? And so the general solution to star is, I'm going to say y sub h, meaning the homogeneous general solution, and that's going to be c1 e to the r1t plus c2 e to the r2t. Okay, so to more or less prove that that's my general solution, I have to do two different things. First off, I have to show that e to the r1t is a solution. I don't have to show that e to the r2t is a solution because it would be the same proof. And then I need to show that if r1 and r2 are different, that those two guys are linearly independent. Okay, so let's do those piecemeal. So I'll call it a theorem. And that is that e to the r1t, comma, e to the r2t are linearly independent. Okay, so how are we going to go about that? We're going to look at the Wronskian. So that'll make quick work of this one. So the Wronskian of e to the r1t, comma, e to the r2t. Okay, so what's that equal? That's a determinant. So we put y1 there, put y2 there, and then beneath it we're going to take the derivatives of each. So the chain rule is going to give me an r1 on the outside. So this would be r1 e to the r1t and r2 e to the r2t. Okay? And just incidentally, I'm using t's here, but x's, t's, it doesn't really matter. Actually my notes say x's, and then I'm here writing in t's. So it doesn't really matter. Just pick your favorite one. I prefer that you not mix them together. So use either x's or t's, but not both. All right. So multiply these two guys, and we get r2 e to the r1t e to the r2t minus, and then these two guys, so r1 e to the r1t e to the r2t. Alright, now remember our rules of exponents. What do we do when we have the same base? We add the exponents. And notice that those two terms are the same in both things. So I'm gonna do all that in one step here. This is going to be e to the r1 plus r2, and I'll put those in parentheses, t. Okay, so that's the common term factored out and simplified a little bit. And then r2 minus r1. Alright, So the deal is that I'm supposed to show that the Wronskian can never be 0. E to the something, never equal to 0. And R2 and R1 are distinct. That's what we made an assumption of. That means they can't be equal. That means R2 minus R1 is not equal to 0. So this is not ever equal to 0, so those two guys are linearly independent. So now I've shown that. Now I need to show that they're actually, actually I already did that. I did that in the last one. Okay, so I'm looking at my notes now and I'm realizing that. So I don't have to show that it's a solution because I did that in the last video that you saw where I talked about the characteristic equation. Okay, so let's just go straight to an example. Okay, so we are going to solve y double prime minus 2y prime minus 8y equals 0. Okay, and here's what I'm going to do. So for this, so most of the time in these videos I'm going to do the general solution and I'm not going to do an IVP. This time I'm going to show you the IVP just so we can see one. They get a little bit more complicated with the other two cases, but the idea is the same. Okay? Alright, so this is going to be really fast, so you're going to love it. So we write the characteristic equation down. That's r squared minus 2r minus 8 equals 0. Okay, and then we factor it. Okay, always try to factor if you can. Don't go straight to the quadratic formula unless you have to. So this is factors of 8 that are different by 2. So that's 4 and 2. It's monic, so both of the guys have r's in there. And that's negative, so 4 is the negative sign. So that means r equals negative 2 and 4. Okay? So essentially here we've done all the work, we just have to write our answer down. So the general solution, and just so we remember, if you don't have an IVP, you're solving for a general solution, meaning you're going to have constants in the answer. And in the first order you have one constant, but in the second order you have two. So YH is going to be C1 e to the minus 2t plus C2 e to the 4t, and I'm done. That's your answer. Okay? Let me get another sheet of paper and we'll turn this into an IVP. So let me do that. So we're going to say that here so we're going to solve y double prime minus 2y prime minus 8y equals 0. So that's my differential equation. And then we need two initial conditions. So y of 0 equals 2. And y prime of 0 equals 6. So those are going to be, for an IVP, those are going to have to be given to you. So the initial conditions are going to have to be given. So we know from previously the general solution is C1 e to the minus 2t plus C2 e to the 4t. Alright, so we just take a derivative of that. Okay, now why are we doing that? Because one of the initial conditions is for y prime. So we need to find y prime so we can use it. So this would be minus 2 C1 e to the minus 2t plus 4 C2 e to the 4t. So that's just chain rule making those constants here. And then I plug the conditions in. So y of 0 equals 2 means that on this top equation, 2 is equal to what I get when I plug 0 in. So 2 is equal to C1 plus C2. And on the bottom equation, y prime of 0 is 6, so 6 is what I get when I plug 0 into that. So 6 equals negative 2C1 plus 4C2. Okay, now that's a system of equations, and look, I like to solve it by doing the elimination, but you solve it however you want to do it. Okay, so if you want to do substitution, that's fine. All right, so I'm going to multiply the top by 2 and get 4 equals 2C1 plus 2C2, and I'm just going to copy the second equation down. And we get that 10, notice the C1's canceled, 10 is 6 C2, so C2 is 10 over 6, which is 5/3. Okay, pretty simple. C1 plus C2 is 2. 5/3 plus 1/3 would be 2. So C1 is 1/3. Okay, now you haven't actually solved the differential equation. You've got all the pieces, okay? So the solution, and so once again, let me just go back and maybe label this. That is called the general solution. Actually, I guess I already did. And this next one's going to be the particular solution. Okay, so it's a particular solution when C1 is 1/3 and C2 is 5/3. And all those depend on, like I said, those initial conditions. So let me give that a name, particular solution. We're going to refer to another type of solution as being a particular solution later. Oops, I guess I could better roll that up so you can see it. But there I've just written the equation with those constants plugged in. All right, that's case 1. Case 2, next.